Hi, and welcome to our presentation on accelerating time to design closure and silicon success for advanced process node SoCs. My name is Wei Li Tan. I'm a product manager for the Solido Characterization Suite at Siemens EDA, and I'm joined today by Henry Chang, Senior Director of Product Management for the Aprisa Group at Siemens EDA. We'll start with a recap of the main challenges on design closure at advanced process nodes and cover the digital methodology requirements for this category of designs and how they're addressed. After that, we'll describe how Aprisa Digital Implementation and Solido Characterization Suite address these challenges, along with results and example case studies of applying these methods in production flows, followed by a summary and wrap-up. Let's start with advanced node design challenges. Digital implementation has evolved throughout the past couple of decades, from 65 nanometer process technology to the latest cutting-edge 5 nanometer and smaller nodes. Due to silicon manufacturing limits, smaller transistor and interconnect feature sizes, and designs becoming more complex in general, several challenges have emerged for digital implementation teams. One of these challenges is pre-route to post-route correlation. As process technology shrinks, wire widths become extremely thin, especially for multi-patterning metal layers. Because of this, resistivity has become the main contributor to timing in traditional flows. This introduces a larger number of iterations needed for design closure and extra margins padded at the pre-route stage, which generally causes over-design and ultimately suboptimal power, performance, and area in the final design. Another design challenge is that the number of process, voltage, and temperature corners, or PVT corners for short, have increased drastically. Coupled with additional sign-off timing modes, this results in more than 100 multi-corner multi-mode or MCMM scenarios that have to be evaluated during sign-off. In addition, the effects of on-chip variation, or OCV, have become a major factor in timing and power and may even exceed the impact of regular timing and power data in nominal liberty timing models. We'll go through each of these in more detail in the next few slides. Let's talk about pre- to post-route correlation first. The semiconductor industry has seen a few paradigm shifts over the years, one of them being the basic considerations for place-and-route. The first generation place-and-route was simply the placement and routing of all instances in the design. Interconnect delay was negligible, and design timing was mainly dominated by gate delay. So if your design met timing in synthesis, you could throw it over the wall to the place-and-route team, and the design would meet final timing without requiring a lot of timing-driven features. This was using what we call a gate-centric flow. That simplicity changed around 180 nanometers when interconnect capacitance started to be a dominant factor of total timing path delay. Here, path timing became dependent on cell placement. This created the need for more timing-driven placement solutions called placement-centric flows. The timing-driven placement had to converge before you could hand it off for routing, but in most cases, the final timing was met without the specific need for accurate prediction of the detailed routing topology. The most recent shift is when moving to 16 nanometer and smaller process nodes. Because of shrinking line widths, particularly in multi-patterning layers, resistance has become more dominant than capacitance in the total path delay, and wire resistance depends on not only the length and width of the wires, but also on the detailed routing topology such as routing layers, vias, and routing patterns, all which needs to be understood in the placement stage in order to accurately predict the timing of your design. This forms the basis of the detailed routing centric approach that we will describe in more detail in the latter section of this presentation. To visualize how traditional placement-centric approaches suffer severe correlation problems between the pre-route timing estimation and actual post-route timing, we use the correlation plots shown. Here, perfect correlation would be a single line at a 45-degree angle, while differences in pre- and post-route timing are noted as points that diverge from that 45-degree middle line. At 65 nanometer, the pre-route Steiner delays versus final routed delays are mostly correlated. At 28 nanometers, the correlation starts to diverge a bit, but is still generally acceptable. And at 16 nanometers, it gets quite bad and can severely impact timing closure and power performance in the area of the final design. Finally, at 7 nanometers, we have an almost random plot where the predicted delay in the pre-route stage almost has no bearing on the post-raw delays. To summarize this point, at advanced process nodes, placement engines cannot produce convergent results without information of detailed routing topology today, which is a shift in the basic factors being considered by traditional place and route tools that assume detailed routing only comes after placement and placement-based optimization. The second challenge we mentioned was the explosion in number of multi-corner multimode scenarios, or MCMM scenarios for short. The number of scenarios in MCMM timing and optimization are based on number of process, voltage, and temperature, or PVT corners, as well as the number of design modes that all need to pass static timing analysis. The biggest culprit behind this rapid increase is the large number of PVT corners needed for sign-off STA. Today, at 7 nanometers, having 50 to 100 PVT corners used at sign-off is quite common. This is compared to only a handful of PVT corners required at 65 or even 40 nanometer designs. There's no longer a best case or worst case corner, so many corners in between have to all be timing validated. Due to the same reasons, optimization at the implementation stage and especially ECO changes have to be internally timed for a large number of MCMM scenarios so that the end result can match with final sign-off STA. In addition, as the number of PVTs grow, we run into an increasingly common issue where the Liberty models for the specific PVTs needed for sign-off STA or MCMM optimization is not readily available. In this case, the design team is left with two rather unappealing choices of either trying to characterize a new PVT from scratch with limited characterization information of the rest of the corners, or applying derates or interpolation to mimic the timing behavior of the uncharacterized PVT corners. Here, we'll illustrate why characterizing missing PVTs is such a challenge. Aside from requiring SpiceNet lists and Foundry PDKs that sometimes are not readily available to digital teams, there is also a significant amount of setup to run a characterization job, which is where factors such as library timing margin and other modification factors are commonly introduced. Without knowledge of this information, digital implementation teams often end up with characterizing a certain PVT only to find that it has a systemic offset compared to the original set of PVTs like shown here. Even worse, these systemic issues are difficult to detect because unless we're looking across PVTs, like shown here, everything may seem correct by looking only at one PVT. On the other hand, as mentioned earlier, using straight interpolation or derates will lead to inaccurate results because these methods typically don't factor in nonlinear behavior within table data or across PVTs. Without a reliable way to obtain .libs at the required PVTs, any kind of multimode multi-corner STA will run into problems, and design teams end up with incorrect timing, power, or noise calculated by STA. This leads to overdesign and schedule delays, or in severe cases, silicon failure. The third design challenge we will discuss today is on-chip variation. To provide some background information on this topic, over the past decade, due to shrinking feature sizes and limits to silicon manufacturing, on-chip variation, or OCV for short, has had a growing impact on design closure. Today, 7 nanometer and 5 nanometer designs can see OCV effects impact timing just as much as nominal timing. At 65 nanometer or 40 nanometers, a flat derate factor was generally sufficient to model OCV. Using this method is very pessimistic because it attempts to capture the worst effects of OCV. However, because OCV effects at 65 or 40 nanometer are generally very mild, this still allows the design to pass timing. As OCV effects increase in 28 nanometers, using AOCV or advanced OCV reduces the timing pessimism by determining the cell's derate based on the number of logic stages in the shortest path, which is slightly more accurate than using a flat derate. POCV, or parametric OCV, increases the accuracy of OCV modeling by introducing a statistical mean and variance to model the variation of a cell. However, each cell is still modeled by a simple mean and variation. At 16 nanometer, 7 nanometer, and smaller process nodes, due to the severity of OCV effects, It's simply not feasible to take OCV into account and still meet power, performance, and area targets with these older methods. So LVF, or Liberty Variation Format, provides the granularity and per timing arc and slew law combination needed to achieve a high level of precision on the amount of OCV applied. As shown here, increasingly granular methods of modeling OCV have been introduced over the past years as a measure to counter the increasing effect of OCV on static timing analysis, with LVF being the most precise and the main method of modeling OCV for advanced process nodes today. LVF is an excellent way of modeling OCV due to providing the ability to apply a precise amount of pessimism to individual timing arcs. How is LVF data characterized though? Well, each LVF table entry technically requires thousands of Monte Carlo simulations, which will make characterization run thousands of times slower. However, characterization tools typically have methods of reducing that to 3 to 10 times of nominal runtime, which is still a big challenge, but feasible. These runtime reduction methods may also make LVF characterized data more prone to errors and may completely invalidate your ST results if the errors are not caught. Because of that, validation of LVF information is extremely important. As mentioned earlier, the impact of LVF on timing and power can be as large as nominal timing, so it can definitely make or break a design. However, it's also very difficult to verify LVF data. Since the data is statistical in nature, what is the correct reference value to validate against? This is the question many library and design teams face. Without the proper tools, LVF data validation may take months and still not catch issues reliably. Here are a couple of examples of LVF data problems. These results are objectively incorrect since statistical timing and power properties of standard cells or other IP isn't supposed to fluctuate wildly like shown here. However, this level of noisiness in .lit data is really quite common even in production LVF.libs. In the previous section, we looked at the design challenges at advanced nodes and how the many factors may potentially introduce design breaking problems if not handled correctly. Now, let's move on to defining a digital implementation methodology that addresses these challenges. What do we need in a digital implementation methodology for it to support advanced process node designs? The first design challenge we discussed was pre to post route correlation.